Welcome, and thank you for coming despite the weather. We are very honored and pleased to have today Dr. Robert Kleinberg from Schlumberger-Doll Research. Bob started his career as an undergraduate student at University of California at San Diego, working on something very nice, which we don't do quite here in the lab, helium-3 and superfluidity at very low temperature. He then moved to, guess where, Exxon. So to the industry, yes, it happens, some of us go there. And then after 2 years there, joined Schlumberger, and since there, he has been working there as a research scientist at their research center. So please welcome Dr. Robert Kleinberg.
See, I'm turned on, yes. Well, good afternoon. It is indeed a pleasure to be here. I've never visited this facility before. I was an undergraduate in Berkeley and worked at what at the time we called Lawrence Radiation Laboratory, and still have my old LRL card, which astounded the guards when I visited there a couple of years ago. The blue LRL, sort of, oh my God, you have one of those. But I've never been here. I've gotten a tremendous education today on what you're up to, and thank you, Paul, for that. It's really, really fascinating. It sort of takes me back to the physics grad student days, which I must say I do miss. Although what I'm doing now is also exciting, as I hope to convince you in the next 50 minutes or so. Just one more word. Boston has famously bad weather. And people complain about it all the time, but when it gets to be its worst, do you know what people say to each other? At least we're not in Chicago. So I am not making this up. So I okay, we have colleagues in Calgary, Edmonton. No, I've been there. I think it's actually worse here. But anyway, so I stand in admiration to your fortitude. My topic today, as you see, is science and technology of unconventional fossil fuel production. This includes fracking. I'm sure you've heard about that in the press. It's been a big sort of issue, and I hope to sort of dispel some of the uncertainties that surround that and sort of basically convince you that although there are problems out there, and we don't deny there are problems, those problems often have technical solutions. And I'm going to be sort of going through a few examples of that and how the industry is improving its performance and really making it safer and more environmentally friendly to produce fossil fuels. So that's kind of the overview. So here's the more detailed outline of what I'm going to be talking about today. First, why are we still talking about oil and gas? I think we all agree we should be on a path to renewables, something that doesn't have a large greenhouse gas footprint, but nonetheless, we're still talking about oil and gas. I dare come here today and talk about it, so why do I have the nerve to do that? Second part of the talk is petroleum geology, which I'm sure is remote from most of your interests, but I think it's kind of one of the most interesting parts of this talk. And then the why and how of hydraulic fracturing, and we'll go into some of the more technical details into how it works, what it does, and the problems associated with it, and how those problems have solutions in many cases. So first of all, why are we still talking about oil and gas? And I think the answer is really encoded in this graph, which is from data from the U.S. Energy Information Administration, which is the main government data collection body for energy. Basically, we have a year from 1950 to 2010 on the horizontal axis, and the fraction of total energy consumed on the vertical axis in the United States. And you can see back in 1850, the U.S. was predominantly a wood-burning economy, a pretty familiar idea. But then as the forests ran out and as coal sort of became available, coal being a denser source of energy and one that's more easily transportable and could run your locomotives, it started coming in with about a 50-year transition time, a little less than that time constant to be precise, but sort of half-decadal, half-century sort of transition to coal. And then back around the beginning of the last century, oil started becoming available, and that too took about a half a century really to come into its own. Although it was even cleaner, it was even more efficient, it was even easier to transport, nonetheless a long transition time. Natural gas in red started coming in the 1930s with a similar time constant, and so on. So it seems like, you know, at the introduction we might have a short doubling time, less than 10 years, but really transition to maturity takes more like 50 years. And the renewables, as of 2010, there's this small sort of green band up here. I hope you can see it. So we're starting from a low base, roughly 2% of our total economy, about 6% of our electric power generation is renewable now. And we've got a long way to go, and it's going to take a while to get there. So in the meantime, we need a source of energy that is cheap, reliable, to power our economy so we have the wealth to make the transition we need to make. I think that's really the main point. Yes?
The wood and biomass can be added to the renewables from some people's point of view?
Yeah, so this is biomass down here, obviously, as you observed. And you could add that to the renewables, but how fast is that going to grow? So I think I'm going to show in the next slide what we expect from wind and solar, and you'll see what my point is. That's a good question. So let's talk about solar and wind. You've probably heard that they are coming on stream, and I must say they're coming on stream faster than I expected. This is brand new data from IHS, which is a industry data gathering organization. This just came out a few weeks ago. They basically predicted the new power build over the next 6 years. And I'll tell you, these estimates are pretty secure because anything that's going to be built in the next six years is probably already baked in. You have to have the permitting, the financing, and all the rest of that stuff. So these are pretty secure numbers. And what IHS is telling us is that about 24% of the new electric power generation will be solar photovoltaic. Solar thermal is kind of in eclipse, but photovoltaic is coming up. It's gotten pretty cheap. Wind is another 25%, so half renewables, and then 40% natural gas, of which about 2/3 of that is combined cycle, which is base load natural gas, and the remainder being combustion turbine, which is peak power. And then everything else is just like small pieces of a pie.
How are you counting the solar and wind? Is this average power or peak power?
This is installed capacity. So the question was, is this average power or peak power? This is nameplate power. Yeah. So whereas these, especially this gas, produces power pretty steadily for base load, these are only on part of the time. So this is nameplate or nominal, but not what it actually produces, which is shown in the next slide. So what we have here is now, from the same report, a graph of years from 2008 to 2020 on the horizontal axis. The vertical axis is the power produced in terawatt hours. So this is what we actually get out of these sources. And you can see that even after all this building in 2020, wind and solar still remain very small pieces of the pie. And with coal, nuclear, natural gas being much bigger. And you can see coal declining a little bit, natural gas gaining, nuclear sort of holding its own. But while the wind and solar are growing fast as a percentage, they are nowhere near to taking over our electric power system. Correct. This is total energy consumed, including transportation sector. This is only electric. That's right. That's right. That's correct. Yes, in the back. Correct. There is no electricity being generated from oil. It is way too expensive. We made that transition about a decade and a half ago. Yeah. Oil's been driven out of that market. Okay, so now let's move on to the petroleum geology piece. I promised this would be entertaining. To understand the rest of the talk, you really need to understand how oil and gas are created. So basically, the start of the petroleum system cycle is that organic matter, algae, dinosaurs, trees, whatever, is laid down in shallow seas and lakes in relatively anoxic conditions, low oxygen, and which preserves it and then is buried. So this purple layer is basically this source rock, which is a combination of organic matter, you know, what I call compressed dead algae, and minerals that sort of co-precipitate or co-deposited with it. And that's basically the source of all our oil and gas. Now, as it gets buried and heated, oil and gas are generated. Oil starts being generated at about 80 degrees centigrade, gas at about 140 degrees centigrade. And because oil and gas are less dense than water and less dense than the organic matter from which they're derived, they are sort of squeezed out, and if they find migration pathways, they will move upwards in the earth. And they will continue moving upwards in the earth until either they hit the surface where they're oxidized and disappear, or they encounter some cap rock, which is shown as gray. And cap rock is, or seal rock, is basically rock typically rich in clay, which has very low permeability to fluid. So it really blocks the further upward migration of oil and gas. And then below that cap rock, there may be, hopefully, a layer of rock which is porous and permeable. Now, rock is like a sponge. It's basically grains cemented together with space in between the grains, and the space can accommodate oil, water, or gas. And oil, water, and gas distribute themselves by buoyancy, with the gas floating on oil, floating on water. And that's your classic petroleum dome. And that's the way we've been basically finding and producing oil and gas for 150 years. That is the tried and true method. Now, recently, and we've known all along, and this is not news, that there is plenty of oil and gas left in the source rock that never found a migration pathway out. But this stuff is very permeable to fluid flow, so you can drill a well and the gas will flow into it or the oil will flow into it. But if you drill a well into this, nothing happens. I mean, we know the oil is there. We can tell from various cores and instrumental means, but it will not flow out because typically the organic matter is co-deposited with the same sort of stuff that makes seal rock, clay, other fine-grained materials which block the flow of fluid. So, trapped. So to sort of further understand where to look for this, we need to know what the Earth looked like when the organic matter was deposited. In the case of the Barnett Shale in Texas, about 340 million years ago. And so you have to know what the Earth looked like 340 million years ago, and it looked like this. Anything that you think you recognize is a false cognate. The Earth has changed considerably since then. Back then, many 100 million years ago, North America was an equatorial continent. Africa was down here in the southern hemisphere. There's a lot of, I mean, China is sort of like a bunch of islands. It's very confusing. Take my word for it. But let's take a more sort of detailed look at the North American part. So, like I say, we were an equatorial continent. In fact, most of the United States, what is now the United States, was south of the equator, shown by this dashed line. The state outlines are, I'm sorry you can't really see it very well on this map, which I got from a publication, but basically New York is here, Pennsylvania is here, Illinois here, and let's see, over on this side, California was an offshore island, Deseret Basin was Utah. Yeah, it could be again someday. And then here's Texas in around Fort Worth. Now, what's going on here is that Africa is threateningly approaching North America from the south and overriding it. But as the continents are colliding, they're creating shallow seas and island arcs. So you have these island arcs here that are similar to the Philippines or Japan today, which are caused by sort of collision of plates. And these shallow seas here are just great places for the deposition of organic matter that's running off this hot continent, hot equatorial continent of North America. So that's sort of the background. So just to look in more detail at this process, this is what's called a burial history diagram. These have a lot of information in them. This is from Tarrant County, Texas, which is around Fort Worth. On the horizontal axis is time running backwards. The present day is here, 0 years, out to 500 million years on the left. The vertical axis is depth, surface at the top, 20,000 feet or 6 kilometers at the bottom. So you can see Barnett Shale laid down in M, the Mississippian, and the Barnett Shale is this purple part. And as Africa overrode North America, that layer was pushed down 14,000 feet during the formation of Pangaea. Now, at 14,000 feet, you can go through the normal geothermal gradient, which is 30 degrees C per kilometer times 4.4 kilometers. Surface temperature 20 degrees C. Temperature 152 C, which is gas formation conditions. So this is where Barnett Shale gas was created back around 220 million years ago. Since then, the giant mountain range that was formed during the collision, the Ouachita mountain range, haven't heard of that one? It's gone. It is gone. Which is why Texas is kind of flat. It was all eroded away pretty rapidly. As you can see, this is the eroded part. And as a result, the Barnett Shale popped up from 14,000 feet to its present depth at about 5,000 feet. So that's kind of the history of the production of gas in central Texas, north central Texas. And by knowing this, and by looking at the maps that I've showed you, it gives you an idea where to look for gas-bearing shales. And basically, the place to look is at the suture between the African plate and the North American plate, which is shown here in this red line. This is the Ouachita Thrust Belt. And it extends from New York State, central New York State, all the way down through Pennsylvania, West Virginia, into Georgia, Alabama, Louisiana, Arkansas, and into Texas. And behind that suture, this is where you find gas shale. And it's one after another. Marcellus, Haynesville, Fayetteville, Woodford, Barnett, and so on. These are all fantastic plays. The shales on this side of the continent have a different origin, different geological history, roughly 100 million years ago, so it's a different story, but sort of similar process. This is source rock, and this is where you find gas today. Yes, exactly. So by knowing a few facts about geology, it unifies a lot of your expectations of where to look for the resource. So it's kind of an interesting story. Let's look a little bit further west of Tarrant County. Eastland County is about 100 miles west of Dallas, Fort Worth. Now here, you're further away from that suture. And the rocks did not get buried as far during the collision between Africa and North America. And so the Barnett Shale, laid down in the Mississippian, now only got pushed down to about 8,000 or 9,000 feet, temperature 100 degrees C, which is what we call the oil generation window. And so you find oil in Texas in the west of Dallas and the gas-bearing area. And in fact, again, if you look at the resource map, and you can see the red is the gas parts, the green are the oil parts, typical oil company coating. You have oil in Ohio and in let's see, yeah, in west of north central Texas, and that's where you find the oil plays. They haven't been pushed down quite so far. Again, these other oil plays have other geological origin, but that's where you go for oil. Okay, so let's look very carefully at what the problem of exploiting this gigantic resource is, because you can see it's all over the place. And this slide really sums it up in kind of three pictures. In the upper left is a SEM micrograph of what I would call a good oil reservoir rock. So you have these big sand grains. These are quartz grains like beach sand. They're it's like beach, and lightly cemented together perhaps with carbonate mineral typically, and these nice big pore spaces. And here's a 50 micron scale bar. You can see the pore spaces in this rock are about 50 microns big, 2/1000ths of an inch. And just to put it kind of on a human scale, human hair is about the same size. So a really fantastic oil reservoir rock produces from pores about as thick as your hair. Pretty remarkable, but true, and it does work. But now look at the pore space in that source rock where you had organic matter, clay, very fine grains laid down together. It's a mess. And the pore space, instead of having these nice big spaces, now is basically filled with organic matter, and the organic matter itself is porous. But look at the length scale. It's not 50 microns, it's 500 nanometers. So these pores are about 50 nanometers in diameter. 3 orders of magnitude smaller. 3 orders of magnitude smaller. Now, those of you who remember your fluid mechanics know what's coming next. And basically, we could put it together in what's called Darcy's law, which is just like Ohm's law. You have a flux, you have a driving force, and a conductivity term, which in the fluids world is divided into a permeability, K, which is a property of the frame and the pore space, and mu, the viscosity, which is a property of the fluid. So the grain space and the pore space is taken apart from the fluid properties, and each get its own term in the conductivity term, K over mu. So let's just look at some of those. And the permeability, if you go through, again, the ordinary fluid mechanics, Poiseuille flow, and so on, you find that the permeability is expected to be proportional to pore size squared. That's very easy to derive. The practical unit of permeability is a Darcy, which is about 10 to the minus 12 meters squared, and a Darcy is consistent with all these units, which you can read for yourself. It's a mishmash of CGS and practical units and whatever. But anyway, that's what a Darcy is. That's what we use. Just to give you an idea of some magnitudes, a water filter at home, swimming pool, might be 10 Darcys. A good oil reservoir, maybe 1/10 of a Darcy. A good gas reservoir, 10 to the minus 3. And this gas shale, the one with the 50 nanometer pores, 10 to the minus 7. Now, the reason why a good oil reservoir can be 10 to the minus 1 and a good gas reservoir 10 to the minus 3 is the difference in the viscosity term. At reservoir conditions, which is hot and high pressure, crude oil typical viscosity 1 centipoise, or 1 millipascal second if you prefer. Natural gas about 100 times smaller. So for a good gas reservoir, the permeability can be 100 times smaller. Simple. Okay. On the other hand, think about the picture I just showed you, that picture, where these pores are 1,000 times smaller than these pores. That means you expect a factor of 10 to the 6th difference in permeability, that R squared term, and indeed, this is 10 to the 6th lower than that. But we only want to get gas out of it, so we only need to make up a factor of 10 to the 4th. You can see why these formations were never considered practical. If a practical flow rate is going to be from a millidarcy, you're not going to get much flow from a 10 nanodarcy. situation. I mean, you're just not, according to the Darcy's law analysis, which is actually holds up for these rocks. So what do? Fracturing. So that's really the whole story. So let's look at some details of, well, first, this is sort of before we get to the details, this is a little overview about oil versus gas. On the horizontal axis, I've plotted permeability from 10 to the minus 8 Darcys to 1 Darcy. Now, just to give you an idea, sort of this reservoir rock that I've been talking about, good quality is up here from 1 to maybe a millidarcy. Low quality below that, and at about a microdarcy, we say it's not reservoir rock anymore. Source rock comes in this lower range. This is the stuff that's filled up with organic matter, clay, and so on, bad stuff. So in the gas world, you get what's called conventional gas, or gas that you don't need fracturing for, down to about 10 to the minus 4 Darcy. For this tight gas regime, you can actually get gas out of permeabilities that are that low by fracturing. And what I mean is drilling a horizontal well, 1 fracture, you're done, go home. And the fracture, which goes out hundreds of feet horizontally, develops enough surface area to the formation to compensate for the lower flow rate that you get in these low permeability reservoirs. So basically, you're opening up more surface area with this fracturing. That's basically the idea. However, for shale gas, with even lower permeability, you need massive fracturing. And on the next slide, I'll show you what I mean by massive. The oil situation, again, remember, oil 100 times more viscous, therefore you need more permeability. Conventional oil ranges here. To get this tight oil, which is in the 10 to the minus 3 to 10 to the minus 5 range, you need, again, the massive fracturing. And the fracturing system for the tight oil and the shale gas are exactly the same. Same equipment, same plan, everything the same. But the difference is the kind of rock you can get it from. Okay, so what am I talking about here? So this is a typical plan for massive fracturing. And to do massive fracturing, you need to drill horizontal wells. Because if you just drill a vertical well, the zone of interest might be 30 meters. At best, that would be a good one. And there's only so much fracturing you can do in 30 meters. If you are able to drill down to the productive zone, turn the drill bit and drill horizontally for miles, 1 or 2 miles, then you can fracture in the productive zone and have many, many more fractures in the productive zone per well than if you just had a vertical hole. That is the importance of horizontal drilling. So I've got some numbers here, and basically this is how you get the 10 to the 4th surface enhancement. You need to overcome the deficit in permeability. And just to put some typical numbers on it, vertical depths are typically 1.5 to 4 kilometers. The horizontal run, 1 to 3 kilometers, actually even more these days. Number of fractures in that, 10 to 30. And then the fracture lengths are hundreds of meters in each direction from this horizontal hole within the, say, 30-meter band of the productive rock. So this is what I mean by massive fracturing, lots and lots of fractures in a horizontal well. Otherwise, it doesn't make sense. So first of all, how many of you are wondering, how the heck does this guy drill wells horizontally? Yes, okay, right. Those of you who didn't raise your hands are either asleep or just tired. But I wondered about it. So I'm just going to spend a minute explaining directional drilling, horizontal drilling, and geosteering. So this is basically, this gets screwed into a drill string. Okay, a drill string is a length of pipe that comes down from the surface, rotated from the top, from this familiar drilling rig you've seen in movies and stuff. That's rotating pipe that's typically about 4 inches in diameter, screwed together, and it goes down. And at the bottom of that pipe is this thing, and then the drill bit gets screwed into here. Drill bit, big kind of 8-inch thing that looks kind of nasty and has lots of teeth with diamond and stuff on it. So basically, this is the part that does the steering. And you'll notice it has these sort of little pads here. I hope you can see them in the figure here. That's what does the steering, and it's sort of explained in the lower right, where each of those pads is actuated by a piston. And the tool is pretty smart. So let's say that you want to steer to the right. So whenever one of these pads is rotated to the left side of the borehole, it will push. And then when the next one comes around, it will push. So basically, these things are actuated to push the drill bit in the desired direction, and basically signals are sent down to it by acoustic coupling with a 10 hertz communication channel. I said 10 hertz communication channel. It's a very slow channel. But an adequate. And there's also sensors embedded in this thing to sort of navigate where it is, so that if you're straying off the mark, it will tell you on the same 10 hertz channel that, oh my gosh, you've drifted out of your zone. So yeah, okay. So the question was, how does it know where it is, metrologically? And there are many methods, and there are some extremely elaborate methods, sort of like radar-type stuff, both acoustic and electromagnetic. The simplest thing to look at is gamma ray. So all these what are called bottom hole assemblies, thing at the bottom of the drill pipe, have a gamma ray sensor in them. Gamma ray is super important because clays are high in potassium, uranium, and thorium. And so the gamma ray signal goes up when you're in a clay. Now, in a lot of these formations, you want to be in the clay. That's the source rock area. So when the gamma ray signal goes down, you know you've drifted away. And then you have to be very clever to figure out, do you go up or down? But like I say, there are some extremely elaborate and much smarter methods that tell you whether you've gone up or down, that are based on ranging, EM or acoustic ranging technology, which is a whole nother talk.
What about absolute position?
Absolute position. Yeah, these things typically have some navigation on them. They have sort of tilt meters in them. And of course, you know how many drill pipe lengths you put down. So you know the length of the drill pipe. And you've kept track of deviations and so on. And that's also included in the basic instrument package sent up on this 10 hertz channel. Yeah?
What sort of radius of curvature can this thing make?
About 10 degrees per 100 feet. Yeah, it's a sharper turn than you think. But you have to imagine 4-inch pipe. I think it's like 1 inch, maybe it's a ½ inch wall thickness. You know, draping that on a pipe stand and see how much it sags, plus pushing it around. Yeah. So yeah, we've actually done better than 10 degrees per 100 feet, but that's kind of practical limit.
I know you're all sorts of things. I'm going to ask you a question I know you solved, but still. So you've got gamma ray spectrometers,
Yes.
electronics, power, computers, and God knows what else, down that damn pipe.
Yes, that's correct. That's correct.
Why is that?
And it's all in the wall thickness of this thing, because you have to keep the centers open for circulating fluid, the drilling mud. So I'll tell you, it's a phenomenal technology, and I hope you will invite me back sometime in the future to talk about the technology piece, which is fascinating. Yes?
Typical RPM?
Typical RPM is about 1 turn per second. Vroom, vroom, vroom. Yeah, okay.
Otherwise 10 hertz wouldn't be enough bandwidth.
No, well, the thing operates autonomously. The 10 hertz channel is only the intelligence that's being sent down. Once the thing is turning, it knows itself which direction it is from magnetometers and so on. And the thing is deployed automatically without command from the surface, obviously. Yeah.
What kind of liquid do you use to transfer energy? Water?
What do you use to transfer energy?
Yeah.
Yes.
Unit energy.
Oh, right. That's at the surface. It's a rotating table on the drilling rig, you know, this big steel structure you see on the...
You transfer it mechanically?
Yes. So it's just like an ordinary drill. You got zzz, you know, it's like you're turning it. That's it. There used to be more elaborate systems where only the bit was turned, but those have sort of gone out of fashion. This is what's called rotary steerable drilling. Rotary because you're using a rotary table at the surface. Yeah.
The acoustics channel is in the drilling mode.
Yes, the acoustics channel is in the drilling mud.
Maybe a different question is, how does the power to the downhole electronics get generated locally?
Yes, it is. So the question is, how does the power get generated to drive all these gizmos? And there's a turbine which runs a generator, and there's batteries and so on. Yeah. But for this sort of thing, basically you've got a turbine system and a battery backup and power leveling. Yeah. Yeah, so the question was, how many degrees of twist in the length of the drill pipe? Lots. I guess I should know that number. Yeah, the drill pipe gets twisted significantly over the 10 to 20,000 feet of the drill pipe. Yes, and there's a lot of friction. I can't give you a number, but I can tell you that that thing is pretty well torqued. Yeah, but you rarely twist off drill pipe. Obviously, it's designed to be strong enough. Although it has happened. Yeah. Okay. Yes.
Well, we are derailing your talk. What happens if one of these things breaks and you lose it?
Oh, yeah.
Drill another one and just leave it down there and start again?
Okay. First of all, the oil company pays Schlumberger for the equipment. I mean, we have got great lawyers. We are totally indemnified. So we get paid. But then what happens is it's what's called fishing. So the question was, what happens if you lose the bit or whatever, any of the stuff in the borehole? There is a specialized technique called fishing. There are special companies called fishing companies. They come down with things that are sort of like, for those of you who remember being a child, these sort of Chinese finger traps. You stick your fingers in, and the more you pull, the tighter it gets. So there are mechanical contrivances like that. You put it on. It's run from the drilling rig, which has a lot of power and torque associated with it. You know, banging, twisting, whatever you need to do. They often get it out. If they don't, fill it up with cement. That's what's called plug and abandon. Yeah. Or drill through this thing, which is called milling. There's options.
The package at the bottom is cheap.
Yes, but we get paid for it, no matter what. You really want our lawyers.
No, we really want to not need your
Yeah, they will. More to the point. Okay, so I'm glad there's a lot of interest in this. Just to finish off the slide, hopefully, this is an actual trajectory, not Schlumberger, but another company, a small competitor. And basically, the objective was to drill between the pink and green formations. I don't know what they were, but they're mineralogically different. And just to give you an idea of scale, this is 8,000 feet to 16,000 feet. So each division is 1,000 feet in the horizontal axis. And the vertical, each division is 25 feet. So there's considerable vertical exaggeration. Again, 25 feet versus 1,000 feet. So you can see that these guys were, this is Brand X, was able to keep right on target, I mean, within a few feet, which is, good. And then here they encountered a fault, a downward fault, where the rocks were displaced by about 20 feet. And it took them a while, but eventually they got back on track using their instrumentation and continued along. So this is, I would call this a pretty good job. So this is an example of how well you can do with modern technology, and not even the best. Okay, now if that generated a lot of questions, we're going to be here for the rest of the day on this one, which is fine, by the way, because I think this is a really important slide, which is why it's loaded with numbers. So what about that fracturing? You've heard a lot about fracking. What is going on with this fracking? Well, okay, typical 5,000-foot horizontal well consumes 5 million gallons of water. One well, 5 million gallons of water, which is about 15 acre-feet, or about 700 to 1,000 truckloads full of water. You use sand to keep the fracture open. Once you've opened it with the hydraulics, you have you have sand that you put into the fracture so that when you release that hydraulic pressure, the rock will tend to close back up. You put sand in to prevent it from closing, so you keep the flow channel open. And you're using about a half to 1 pound per gallon, so now we're talking about millions of pounds of sand. And chemicals, you know, the industry likes to say, oh, it's only 1%. Well, 1% of 5 million gallons is 50,000 gallons. That's 50 more trucks. So lots and lots of everything. Now, as far as the pumping is concerned, typical pumping rates, 4,000 gallons per minute at 10,000 psi, 24,000 horsepower. Each of these red trucks, Halliburton trucks, provides about 2,000 horsepower. They are operated at about 75% efficiency. You need spare trucks because the trucks are always breaking down, Halliburton. So it takes about, we do that too. It takes about 20 trucks to fracture a well. What you're seeing here is 40 trucks that are actually fracturing 2 wells simultaneously. It's called the zipper frac. Yes, these are pumpers. These are pumpers. They are collectively pumping. Each group of 20 is pumping the 4,000 gallons per minute at 10,000 psi. Where's the well itself? There are 2 wells actually. One is they're here and here, I think. Let's see. It's kind of hard to see in the picture, I must say, but they're sort of centrally located. Is there a reason they're so close together? They can be. I'm going to show you in a minute that nowadays it has become very popular to drill many, many wells from one position. If you have this steering capability, you can start from anywhere and go anywhere. Really, and that is super important, as you'll see in a minute.
What's the pressure at the bottom? The ambient pressure from the overhead rock?
Pressure at the bottom is the 10,000 psi wellhead pressure plus the hydrostatic head of the water, down to whatever your 5,000 feet, 10,000 feet, whatever it is. So downhole pressure is going to be 20,000 psi, that range, 25,000 feet. It depends on the depth of the well.
No, differential pressure that does the fracturing, so that's the well.
Exactly. This is 10,000 psi plus your hydrostatic head. Right. Correct. Yeah. And that has to overcome the lithostatic load, the horizontal stress in the rock. That's correct. That's why you need the extra 10,000 psi. Precisely. Yeah.
So, depending on the geology, you could drill radially in a certain type of situation like this.
Could. Yeah, could. That hasn't been done. I'll tell you why it's not done that way. I don't have in another talk I have sort of well trajectories, but generally what you want to do is you want to drill along the direction of maximum you want to drill along the direction of minimum horizontal stress in the Earth. Now, the Earth has 3 stresses. Vertical stress, normally the largest, and then 2 horizontal stresses. It's a tensor situation. Basically, when you fracture rock, you are going to be opening up the rock normal to the minimum stress in the problem, the minimum horizontal stress, typically. So if you drill a well parallel to the minimum horizontal stress, your fractures are going to be parallel to each other and perpendicular to the borehole, and that's exactly what you want. So people do geophysical, geomechanical studies to figure out what the stresses are in the Earth, and then you drill along the minimum horizontal stress direction. So you don't tend not to drill in circles. You could, but that's not practical.
So this looks like great technology to drill under your neighbor's property.
Absolutely.
So how do you, are you required to document in any way where the end user?
Of course you are. Yes. No, I mean seriously. So the yeah. So the question is, what prevents you from drilling under your neighbor's property? And the answer is nothing. But yes, I mean, you have to file with your state a drilling plan, and you have to know where the end of your well is. Now, how far those fractures go out, who knows? But what tends to happen is that with these resources, basically you're developing a square mile at a time. That's kind of a usual kind of grid block in the United States. And so you have to basically go to all the land owners, homeowners up there, and you've got to buy leases from them individually. Now, let's say that your 20 nearest neighbors have, sold leases, and then you've got one in holding. That can be taken by eminent domain, according to state law. Fascinating litigation regarding that. Eminent domain means that you get paid the fair market value for the lease, which is kind of the average of your neighbors. Yes?
In some parts of the country, subsurface rights were sold off years ago, never developed, and then reverted to, like, I don't know the correct name, but reverted to the public domain or whatever anybody liked. Are you in an environment, are you working in places where that's true?
So,
you tend to be places where they were never settled?
so the question is, what happens when the subsurface is owned by different people than the surface? That's what's called a split estate, technically. And so basically, in the United States, the subsurface does not revert to the state except under public land. So anything on private land, the subsurface down to the center of the earth is also in private hands. Now, it doesn't have to be the guy that owns the house at the top, but you have to go to whoever owns the mineral rights, the appropriate mineral rights, and get the lease from him. And of course, the homeowner can be extremely pissed off because there's stuff going on under his home and he's not getting anything. It's even worse in Europe, where the subsurface is owned by the state, in fact. And there, countries like the UK are trying to figure out how to pacify the landowners and the people who live at the surface, who are aware that they've got to deal with this massive industrial operation and they don't get any royalties from it. So the UK government has plans to sort of give money back and so on. There's various plans for making it palatable to the public. If you don't do that, you wind up with France, where they just don't permit it, which is where France is today.
This fracturing is done all at once. Fracture the whole length.
No. You do it in stages, about 400 feet at a time. So the question is the fracturing done all at once? No. It's done one at a time. You fracture 400 feet, block that off, next 400 feet, block that off, next 400 feet, and up along the well. Yeah.
So you drill just
Yeah, the whole well is drilled, and then the the method for only fracturing part of the well at the time is really interesting. In view of the hour, I'm not going to explain it in detail, but we can talk about it later. But there are some very
maybe
clever
one last
methods.
question from Rick, and then we allow our speaker to finish his talk.
Oh, okay. As far as I'm concerned, I can stay here all night, but probably most of you don't. Yes, okay.
This is a related question to one that Bob asked.
Yes.
North Dakota and eastern Montana, a lot of those lands Native American.
Yes.
Does that present additional problems?
Yes.
Drilling and such?
So the question was, what happens when the Indians own the land? Yeah, then you got to deal with the Indians. So I think in practice this has not been a problem because, there's a lot of money in the oil and gas industry and enough to buy off the people owning the mineral rights. So I would say I don't know of a case where there has been specifically an Indian land issue. There could be. I'm not saying I know every single lease situation.
Part of the reason I'm asking the question is that the drilling stops at the border between North Dakota and Montana. Across the border in Montana, it's easy to
So the point was made that the drilling tends to stop at the North Dakota-Montana border. True, but that's actually more geology-driven than legal. It turns out that the heart of the Bakken Formation, the one that you really want to drill out, is in North Dakota. Very little gets into Saskatchewan. Very little gets into Montana. Yeah. Yeah. Okay. Nothing more to say about this. Okay. Let's look at some of the environmental issues. And again, I realize the lateness of the hour. You feel free to leave. I will not be offended. But on the other hand, stay all night. But this is what I call the environmentalist perception of gas shale and tight oil development. If you have sort of trawled the web about fracking, you've probably seen this picture. This was on the Union of Concerned Scientists website, and I must say I who are also in Cambridge, and I went over there and criticized them for posting this because this is not a gas shale development at all. This is, I recognize this as the Jonah Field in Sublette County, Wyoming, which is a conventional gas play. These are all vertical wells. This is what happens when you develop a field with all vertical wells. 33 square miles of this gas field, 16 to 32 vertical wells per square mile. We're talking about 1,000 wells, all going straight down. This is not massive hydraulic fracturing. This is exactly what you don't do when you have horizontal drilling. And in fact, an environmental organization in Wyoming sued the developers of this field, and on the grounds that they should have used horizontal drilling. And there would have been far less disturbance, and they were darn right. Now here is a more typical, and I call this modern best practice, but in fact this is really, it's not just best practice, but it's common practice at this point. This is modern best practice for this gas shale or the tight oil, which is the equivalent sort of oil resource development. This is at the University of Texas Arlington in the green shaded 5-acre well site where all the drilling was done, where all the fracturing was done, right off the campus. They drilled 19 wells from that, drilled and fractured 19 wells from that 5-acre site. And you can see the wells are going underneath the central campus into this, what looks like a light industrial area, and even a well sort of underneath what looks like kind of a nice residential area. So this is kind of an example of what you can do. You can basically produce from several square miles from a single 5-acre site, which is about 1/100th of a square mile. Now, how big is 5 acres? Maybe you country guys know, but 5 acres is about the size of a Walmart supercenter. Just the store, not the parking lots, not the other stores, not the satellite stuff, not the highways, just the store, 5 acres. So that's basically the land that you're taking up. When you're done with all this heavy industry, you take it all away. And let's see if I have this. I don't think no, I didn't include this slide. You take it all away. All you have left is a pipe coming out of the ground, going through a valve, and going back into the ground to another pipe, and that's it. And then you can plant grass, put up barns, whatever. So the land use issue is not so bad, not as bad as it's made out to be by some. Now, what about the water issue? 5 million gallons. How much is 5 million gallons? It turns out to be about 5 Olympic-sized swimming pools. Sounds like a lot of water. With the dimensions 25 by 50 by 3, that's a deep pool that they had in London. So that's kind of impressive, and you're using this for every single well. Problem. Yeah, don't.
Per day, right?
Per well. Per well. 10,000 wells a year drilled in the United States. Okay.
Presumably you pump that water in, you pump it back out.
You don't. You get back about 1/3, and what you get back you do not want to use. It is toxic wastewater. So it is a true withdrawal from your hydraulic system. Even if you get it back. Of course, if you get it back, you can reuse it. Okay. So, but let's look at what 5 million gallons means. And everybody's impressed by that except farmers who say, what? Why are we talking about this? Just to give you an idea of magnitudes, about 10,000 wells a year are drilled in the United States. At this point, most of them are shale wells, many horizontal. 15 acre feet, 5 million gallons is 15 acre feet, which comes to about 150,000 acre feet per year. That would be a high upper bound estimate because I'm using the high upper bound of this number. Let's compare that to the water used to irrigate crops in California. California being in a drought, I'm not saying these numbers are not for this year in particular, but this is typical of California. 34 million acre feet a year. How much water is used to irrigate alfalfa in California? Just alfalfa, 5 million acre feet a year. Now, I'm a San Francisco guy. I grew up with Altadena dairy. I love dairy cattle that eat alfalfa, but come on. If you are worried about 15 acre feet of water per well, that's your problem. So I think the water is something we can manage. Let's see if I have another slide on it. Nope, I don't. But although water may not be your problem, the trucks will be your problem because 5 million gallons is about 700 to 1,000 trucks, and that's round-trip truck trips on your roads per well. So this is displayed very graphically by this aerial view. It's rather old. It's from 2006, back in the early days when they were only using 3 million gallons per well. But what you're looking at are water tanks, each of which can handle about 4 truckloads of water. There's 150 of those water tanks. I counted every single one, which means 600 water trucks of 5,000 gallons each. So tremendous amount of truck traffic if you use trucks. So this is a problem, and this is what people actually wind up complaining about. Okay, now I've already said that the water that you put in, isn't necessarily so bad, but what you get out is very saline, somewhat radioactive. That's because it's basically groundwater at that depth of 5,000 to 10,000 feet, which is very mineralized. Plus you've got the hydrocarbons. So can any of that get into the drinking water aquifer? This is a big question. As far as direct contact between the well that you're fracturing and the aquifer, I would say rarely, if ever, and maybe never. This illustrates it. This is a little bit hard to interpret, but this is data from, again, the Barnett Formation in north central Texas. The horizontal axis is depth, and the dark blue is the depth of drinking water aquifer at a location, and the deepest are a bit more than 1,000 feet. This is below that, the water is not usable for agriculture. It's too brackish or just outright saline. Each of these data points here represents a well at a given depth, and the lines that you see above and below are the extent of fracturing. And we know how far the fracturing goes above and below from what's called microseismic, which is basically monitoring the acoustic emission of the fracture extension. So every time the fracture extends, there's a crack. We have geophones located uphole, downhole, and you can triangulate, just like an earthquake, back to that fracture extension event. And so you can tell how far you're fracturing, and as you can see, there's thousands of feet of rock between where the fractures are and where the drinking water is. Now, I will not say you can never have a direct contact. There are some famous cases where there seems to be, where the gas-bearing or oil-bearing layer is much closer to the drinking water aquifer. Pavilion, Wyoming is a famous one. But generally speaking, it's not so much of a problem. I'll tell you what is a problem. Yes. Yeah, well, these are, you mean far right. Oh, this. No, I think it's actually, I think it's the frame of the plot. There is no drinking water that goes down to 4,000 feet. Yeah, no, there is no drinking water that goes that deep. Okay, so let me tell you what is the problem. What is the problem is when you drill the well. Drilling a well is kind of like taking a hypodermic needle and sticking it into your skin. If you don't use sanitary measures, you will get an infection. Something will come in from the top and infect you. In the well case, you can have pollution from the surface, some sort of surface spills, industrial accident type thing, at the well site, perhaps. And from below, you could have either the hydrocarbon you're producing or else methane, which is sort of pervasive in the subsurface. So the way the oil industry prevents pollutants from getting into drinking water aquifer is by putting down steel pipe and then cementing the pipe. Now, the steel pipe is obviously pretty darn impermeable, but the problem is fluids coming up outside the steel pipe up and down. So the cement is designed to seal off that annulus between the steel pipe and your precious drinking water formation. This graph, which comes from a Schlumberger publication, autumn 2003, is an illustration. It was also, no, it wasn't, kind of shows exactly what the situation is. You might have a shallow gas zone. Here you've got good cement in the drinking water zone, which is this brown area, and nothing comes in. You know, if gas comes up, it's confined, so it does not get into the drinking water. But on this side, where you have a gap between, say, good cement and the brown formation, then you have these pathways through which gas, oil, or polluted water of some sort can get into your water well, and that has been observed. So, what is the answer? Well, no, before I get to that. Here's part of the question. This is not the answer. This is another bad cement job. So you probably, I guess I should have rehearsed this more this morning. You probably remember this picture from the Deepwater Horizon, the Macondo well blowout in the Gulf of Mexico in 2010. This was caused by exactly what I just told you. Inadequate cementing, allowing oil and gas to come up, in this case to the seafloor, which is a really bad thing. Blowout, lost the rig, 11 lives. Bad, bad, bad story. Halliburton cement. It was. We have a better cement system, and I don't think it would have happened with ours, but anyway. Okay, so this is a problem that is solvable. Now, remember, the idea is that you want to fill up that space, that angular space between the steel pipe and the formation. Now, your ordinary Portland cement, you probably know this, shrinks about 0.4% when it cures. So that is the worst possible thing you could have in this situation, because as the cement cures, it's going to retract from that formation and open up what's called a microannulus, which is just a basic pathway right up into your drinking water. So Portland cement's bad news. So, but there are ways of putting additives into cement to solve this problem. So one is an expandable cement, and that's not a new solution. Good old magnesium oxide is often used in cements to make sure that they do not shrink and maybe even expand when they cure. So that's step one. You absolutely need an expanding cement. You also want a flexible cement. Why? Because after the cement has cured, basically if you flex the steel pipe, for instance, by applying 10,000 psi to it, you have a fair chance of cracking the cement, because at this point cement is brittle. So, however, by putting in stuff like polypropylene as an additive into the cement, you can make the cement flexible enough so if the pipe sort of expands as a result of this 10,000 psi stuff, the cement is flexible enough to sort of follow along. But let's say a crack of some sort does develop. We, Schlumberger, have actually developed self-healing cements. So there are additives that will swell in water, in contact with water. So let's say you have that microannulus or a crack, and water is flowing up, polluted water, say. This, if you put in polyacrylamide or polymethacrylate into the cement, it'll swell with the water, causing the cement to swell and seal up the water. And I actually have proof that it does work. And there is even self-healing cements that self-heal in the presence of hydrocarbon, oil, and, believe it or not, even gas. Rubber is one. Alkyl styrene is another. These things, in the presence of hydrocarbon, swell and, again, close up the crack. And this has been documented. And, of course, we have patents. So we can solve the cement problem. Are these always used? No. But they could be used. So this is kind of the difference between, you know, what technology can provide and what the marketplace will accept.
Could you tell us what the federal or state requirements are with respect to this issue and what are the prospects for improving that?
Yeah. You know, the oil industry has fiercely resisted any federal regulation of anything having to do with oil and gas. I mean, fiercely. But the states are the primary regulator, and they have regulations on where to place cement. As far as regulations on cement compositions, I don't know how far that goes, and it might vary state by state. What I do know is that even if, say, this is mandated, it might be, and maybe oil companies even would want it, these three are not. These three are considered options. Yeah. Yeah, that is the right measure. I cannot give you those numbers. I can't give you the price list even if I knew it, because we don't publish our prices because we charge each client a different price. This is the reality. But I will tell you that these cements are significantly more expensive than their conventional counterparts, and that is a problem.
But how can the cement really be a significant fraction of the overall drilling cost?
No, 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 no. Especially if you're only concerned about the cement in that narrow region of drinking water aquifer. You don't need, I mean, what happens down below, who cares? I mean, it's kind of technical whether it's cemented or not. But the drinking water aquifer is the really important part. And really, for that small distance, it might be a few hundred or 1,000 feet at the most. No, it shouldn't be that expensive. So it's a little frustrating.
We have a few more slides to go, so.
We have a few more slides to go. Actually, I think we're almost at the end. Breathe a sigh of relief. Yeah, so I just want to end up with what these resources mean in terms of our energy outlook in the United States. There's an equivalent slide for gas, which I have not included in the interest of time, but this is the oil picture. Again, 1980 to 2035. These are projections from the International Energy Agency, very reliable World Energy Outlook. Vertical axis is millions of barrels per day produced in the United States. And as you see, we have been on a long-term decline up until about 2005 in our oil production. This is not a secret to anyone. It peaked out in 1970 until this tight oil thing came in with the massive hydraulic fracturing. Now, that has really changed the game. Basically, what has happened in the last couple of years is that we have replaced the oil output of Iran. When we embargoed Iran, we took something like 2 million barrels of oil off the market, along with our European allies. We replaced those 2 million barrels ourselves. That's remarkable. That is a remarkable statement. It was pointed out to me by Jason Bordoff, who used to be in the White House. So it's not just the tight oil, which is this big red bar here, but it's also natural gas liquids, which come from similar plays. And you can see that that's been expanding. And this is sort of your ethane, propane, butane, pentane fraction, which basically is chemicals. Well, you know, this is the projection. I'm glad you asked that. The question was, is it all going to be below 1980 by 2035? This is the projection of the International Energy Agency. Personally, I think they're being too conservative. We do not know the extent of this resource. Nobody knows the extent of this resource. They are looking at the known resource and making a reasonable projection. So I'm not sure which way that's going to go, to be honest. But that's a good question. Okay, just to sum up. As I told you earlier, on a national scale, energy sources change slowly. And oil and gas will be an essential part of our energy mix for decades to come, despite the fact that we are building out wind and solar just about as fast as possible. Paleogeology unifies our understanding of the continental scale distribution of oil and gas reservoirs. Shale gas and tight oil are produced from rock formations having very low fluid permeability, and hydraulic fracturing makes production possible by increasing reservoir surface area by a factor of about 10,000. And finally, hydraulic fracturing, as you saw, is an industrial scale operation, but environmental questions are being answered by continuously improving technology. We haven't solved every problem, but we are trying to solve them. So with that, thank you, and I appreciate your attention.
Thank you very much. Yes, there are more questions. People that have been patiently waiting.
Okay. My flight isn't until 9, so go at it.
That's so many questions. It's hard to figure out which one to ask. I mean, you made it sound like the easy stuff is a very unusual coincidence. The stuff that we've been able to find and tell us. Is there any idea for the relative scale of what might possibly be available at these deep levels?
Yes, and that sort of comes back to the previous question. The answer is we don't have a good handle on it. I mean, you're right. The conventional oil, we've been producing for 150 years, is easy, but it's in small reservoirs which are created by lucky coincidences. This is pervasive, and it's what the United States Geological Survey calls a continuous resource. It's more like coal. You get down into that formation, and you can drill, drill, drill. That's why it's developed a square mile at a time. So I would say we do not have a good grasp on how much we have in the United States, and even less overseas. We have really no idea what the international resource is. I mean, the EIA has published estimates, but no one really believes them.
Relative to what the total amount of oil was extracted, is it the same scale or 10 times more, 100 times more?
The question was, is the amount of oil and gas and shale comparable to our conventional resource? And I have no idea, and no one has any idea. I could show you the IEA estimates, which show that these resources are small compared to conventional, but we are 5 years into this. We are 5 years into this. So we don't know. We don't know.
What do you do with the polluted water? Because you said that the problem is the trucks, a lot of water that comes back polluted and everything,
Yeah.
even radioactive. So what do you do with it?
Yeah, okay. The water that comes back is pretty much toxic waste. I mean, let's not put a fine point on it. So, okay, there's a couple of things that can happen. First of all, the most common thing is it's put into what are called disposal wells, which is the way toxic waste is normally handled, which is a well drilled down into a saline aquifer with water similar to the water that you're disposing of, basically. Highly saline, radioactive, et cetera, at very deep depths, more than 5,000 feet. Now, that works in Texas, which has 12,000 of those wells. It doesn't work in Pennsylvania, which has 6 of those wells. The reason is that subsurface geology of Pennsylvania cannot take up fluid that you pump into it. It's all metamorphic rock. It's the base of the Appalachians. So in Pennsylvania, they've had to truck the wastewater, hundreds of miles to Ohio. That is really expensive. So what the industry has done is they've taken that wastewater, which is about a third of what you pump down, about a third comes back, and called on Schlumberger to purify it. So we give them back water that they can use in the next well. And that works. That works fine. And it costs them some money, but it's less than transporting it by truck.
What does purification mean? Suitable as a drilling fluid.
What does purification mean? Exactly. It is suitable as a drilling fluid. It is not at a condition that it can be discharged to the surface waters. It is not. It is highly saline. It might be 10 times more saline than seawater, for example. Could be. Still have the radioactive stuff in it, maybe. You've taken out the oil and grease. You've taken out the stuff that would basically mess up the formation if you pump the stuff back down. But that's very minimal processing. To give you an idea, we would charge $1 for 42 gallons of this purification process. Okay. So it's very basic. It's not desalination at all. But that's good enough. That's good enough because we have chemistry, fracture fluid chemistry, that can accommodate it.
Okay.
Wells with this special cement for those poor people that have gas in their drinking water. I mean, I'm sure you would love to sell more of these chemicals.
Absolutely.
Cement, but is there any way to fix wells that have already developed this problem?
So the question is there any way to fix wells that are leaking? Yes. It's what's called a squeeze job. It even has a slang term associated with it. And what you do is you drill through this is going to sound weird, but it happens. You drill through or blast through the steel pipe at the location where you have the leak, and that can be determined by acoustic means, by acoustic reflection means. Drill through there, and then put in cement under pressure to squeeze it into the gap. And that works, you know, more often than you might expect, actually. Yeah. So wells are fixed that way, and it's kind of semi-routine.
But it interrupts production.
Of course.
So when you drill into a formation and you frack it, when you're all done, what fraction of the oil or gas in that formation are you actually removing?
Are you in the industry? Good question. Really low. There's a whole nother lecture about what you actually get out of these wells and how you get it out. But in oil plays, you get 5 to 10% of the oil that's in there. In gas, you get, these days, maybe 15% of the gas that's in there. And the reason is that you've made all these fractures, you've increased the surface area, but still the transport of oil or gas to the fracture is extremely inefficient, extremely slow. So you get very little of what's there, which has raised this question inside the industry of how do we get the rest, and have we messed up our oil fields? With respect to the remaining 85, 90%, it is a serious, serious question. Serious question. Yeah.
Excuse me. What was the technological breakthrough in 2006 that enabled all this, and why was that not foreseen by energy policy makers?
Yeah. Okay. So, you know, we've had horizontal drilling since the 1980s. We've had hydraulic fracturing since the 1940s. So, and also, due to studies done by the Department of Energy in the 1980s, we knew that there was a lot of oil and gas in these shale formations. I mean, there was this Eastern States Devonian Shale project that went on for 10, 15 years, whatever, that absolutely demonstrated this. Basically, this may sound dumb, but nobody actually put all this stuff together. I mean, the paradigm was either you drill a vertical well and fracture it, or you drill a horizontal well and don't fracture it and just use natural fractures. And this was the mindset, but this, and then shales were completely nonsense. I mean, you know, 10 to the minus 7 Darcy, forget it, no way. But this guy, George Mitchell, and it was really one man, who said, no, I'm going to get oil and gas out of these formations no matter what. And he just tried one thing after another, and he came up with this idea of combining, sounds obvious, you know, in hindsight, horizontal well and then many, many fractures along that well bore, with the well bore drilled parallel to the minimum horizontal stress so that the fractures were all perpendicular to the well bore. And then basically packing them off so you could do multiple fractures in one well bore. That was kind of another step forward, because you need to be able to fracture this little piece, then this little piece, then this little piece. Otherwise, you just make one fracture and that's it, right, if you just have an open well bore. So, and I'll tell you, it took till 2006, 2007 for this to sort of sink in. I worked on the National Petroleum Council report to the Department of Energy in 2006. Shale, in this 250-page report, shale got about 2 paragraphs. I mean, and we had like the industry experts, I'm not including myself, the industry experts working on that chapter. It was totally missed, totally missed. But this is an example of the inventiveness of a person. Hope springs eternal.
So it was reported back in, I don't know how many years ago, that Marcellus shale drilling resulted in flammable water.
Yes.
Can you talk about how many sites in that day let that happen, and today how many sites are letting that happen compared to the different kinds of drilling we have now?
Yeah, that's also a very good question. Basically, an organization called Tudor Pickering, which represents investors, so they don't really care, they just want to make sure their investors don't invest in stupid things. They actually looked at the environmental issues that were reported in Gasland. And I think they had a big table. It included everything in Gasland plus other stuff. And they systematically looked at what the state regulators had found as the root cause. Often it was this bad cement job business where, which caused a lot of this migration of either production gas or just gas that's in the subsurface ubiquitously, migration into the drinking water aquifer. They also identified some cases of spilled chemicals at the surface, cases of people disposing of this wastewater in streams, which is illegal. So as a result of Gasland, the movie, and reports like this, I'll tell you, in particular, state of Pennsylvania really tightened up on a lot of this stuff, and a lot of this got sort of tamped down. The worst abuses certainly got suppressed. But in terms of how many incidents there are, it's been hard to track because the states do not have uniform reporting standards. Each state is different. Some are crazily hard to find that information. I think anecdotally, it seems like things are getting better, but I wish I had real statistics to give you. The University of Texas looked at this. They sent out a corps of law students to all the states to try and figure it out. They came back, and you should read their report. It would make you cry, as a scientist, that the information gathering is so difficult. No argument there. Yes.
Or companies done with the well, do they seal it up in such a way that you can come back in 10 or 15 years when the price of natural gas on the market is doubled, or the next technologies come along, or have they, locked the door and thrown away the key?
Yeah, both. So the first scenario is called shut-in, where you take that valve. I told you there's a pipe coming out of the ground with a valve. Close the valve. Okay, you still got the gas well. It's not flowing, but you're keeping it in reserve, waiting for the price to go up, or technologies to clean out the well and do something better. Absolutely. Point number, the second option, which you presented, is called plug and abandon, where you fill up the well bore with cement and walk away. Yeah, so both happen. It's sort of, it's hard to, so the question is there a lot of the shut-in? There is a lot of gas shut in today because the price of gas is low. I cannot give you numbers. I mean, those numbers are probably more accessible than the environmental issue numbers, but I don't have them in my head. Yeah.
You told us that the fracking stuff the fracking fluid is got 1% additives.
Yes.
You told us that there's a lot of nasty stuff. A third of that water comes back out, but you didn't relate the two. Are those additives really nasty when they come back out, or are they just minor component of the nastiness that has to be dealt with?
Yeah, the latter. They are minor components of the nastiness that comes back. Yeah, so what you're putting in is a slate of chemicals, and some are completely harmless, some, okay, intermediate, whatever. You don't want to spill this stuff on the surface, definitely. But what comes back is really much worse, because deep groundwater is very mineralized. I don't know, I used to live on Limestone Road in Connecticut, and believe me, you could tell that. And that was, of course, drinking water, from my 35-foot deep well. So this stuff comes back pretty nasty. There is some fracture fluid chemical in it, but that is not the main problem. There are ways of just sort of cleaning that up routinely, again, for the reuse issue. But most of it is just the high salinity issues. And especially divalent ions are really nasty for reasons you can guess, scaling and so on.
Let's thank our speaker. This was a very good conversation.